Okay, so in the last lecture we had discussed about this thing that suppose X does not belongs to A closure, then from here we can imply that X belongs to X minus A interior. Okay, or rather we can say X belongs to exterior of A, and the converse also. Okay, so this is a biconditional statement. So now suppose A is a closed set. A is a closed set. So A being closed set, we have A closure equals to A, right? We have A closure equals to A, and from here we can say that, so since this is a biconditional statement, X not belonging to A closure means X belongs to capital X minus A closure, and being a biconditional statement, this must equal X minus A interior, while A being closed, A closure equals to A. So from here we have X minus A equals to X minus A interior, which eventually implies that A is closed. A is closed if and only if X minus A is open. So this is a very important theorem. We have kind of proved the theorem already. Okay. So for a set being closed, the complement of the set is open and converse. Okay. Is it clear? Okay. Achha, what is an isolated point? Isolated point is basically a limit point. An element of the set which is not a limit point. Okay. X belongs to A is an isolated point. Is an isolated point if X is not a limit point. Okay. So an element from a set, if not a limit point, is called an isolated point. Clear? Clear? Okay. For example, let's say we have this set. Let's say we have the metric space Rd. D is the usual metric space, and let's say we take this set. A is 1, 1 upon 2, 1 upon 3, and so on, 1 upon n, and so on. Okay. So it is pretty much evident from here that A closure equals to A, that is A is a closed set. What is the only limit point here? The only limit point here is 0. The only limit point here is 0. There is, so basically every element of A is not a limit point. So what does that mean? Every element of A is an isolated point, right? Every element of A is an isolated point. So in my previous lecture I have already discussed what limit points are and what closure points are. So please do a look at those things. Okay, so are these things clear? Okay. So now let us check a very important proof. Like in case of open sets, we had proved that every open ball is an open set. So in this case also, we have every closed ball is a closed set. Okay, this is a very important theorem. Every closed ball, every closed ball is a closed set. Okay, every closed ball is a closed set. So in case of open balls, we had proved it. In case of closed ball, we are going to prove it now, and the proofs are fairly similar. Okay. So let us first choose a closed ball. Let's say let xd be a metric space. Okay. Let xd be a metric space. Let small a belongs to x. Then for all r greater than 0, so we define a closed ball with centroid and radius r, and we already know the definition. I'm again writing it. So it consists of all those elements such that distance between a and x is less than equals to r, right? Okay. So see one. So what we need to do is basically we need to prove this to be closed. Or we can do one thing, since we have already read much about open sets, we can also try to prove this to be closed using the concept that x minus b ar is open. Okay, that is one thing which we can do. Okay, so let's see. So suppose we choose an element from this. Okay, so let y belongs to x minus b ar. Okay, so what can we prove? We can prove that an open ball centered at y and radius, let's say delta, it is completely contained in this set, proving this to be an open set and bar to be a closed set directly. Okay, acha. Now if y belongs to this, so we can obviously write that distance between a and y is greater than r, right? So I'm giving you a visual representation of it, considering this to be an r2 plane and this to be an usual metric. So suppose this is bar. Okay, this is the center a, and this is a point y which is outside bar. So this distance is obviously greater than r, right? Is it clear? Is it clear? Acha. Now what we will be doing is that we will choose a certain positive number delta. We will be choosing a certain positive number delta. Choose delta greater than 0 such that distance between a and y is greater than r plus delta. We can obviously do this. We can obviously suppose delta is this much. Suppose. Okay, there always exists a positive number such that we can write this statement. Right? Right. Okay. Now, 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 suppose Z belongs to an open ball centered at Y and radius rho. Okay. Then dZy is less than rho, or we can say dZa, which is obviously less than equals to dZy plus dy rho using triangle inequality, and dy rho uh, dy rho is less than, so this is less than sorry, am I doing something wrong? Sorry, dy a, sorry, not dy rho, dy a, yeah. So this is less than r plus rho, this is greater than r plus rho, this is greater than r plus rho, and this is less than rho. So they eventually give you the value that this is greater than r, right? This is greater than r. So this being greater than r obviously implies that that so distance between z and a, distance between z and a is greater than r. So this means an open ball centered at y and radius rho is completely contained in x minus bar, reason z was an element of u y rho. Is it clear what I am doing? See, this was bar. Okay, this was y. We made this. Okay, this is rho, this is r. We choose a point from here, let's say z, and we proved that this distance is greater than r, which eventually implies that z is outside this and z was an element of this. So what does that mean? That means that open ball centered at y rho is completely contained in x minus b. So what does that eventually mean? So this eventually means x minus bar is open, which implies bar is closed. Is it clear? Is it clear? Okay. And what can you tell about singleton sets in a metric space? They are closed. Okay. in any metric space, singleton X is closed. Okay. Also to be remembered, in R, if a set is closed, it contains its bounds. Okay. If a set is closed, it contains its bounds. That is its upper bound and its lower bound. Is it clear? Okay. So now we discuss a little bit about Cantor set, and then we will be moving on to the concepts of sequence spaces. Okay. Okay. So Cantor set. Okay. So Cantor set is basically a set which is very famous in measure theory as well as in topology. So it is a set whose measure is zero. Whose measure is zero. Okay. We are not going to discuss what measure means, but you might think of it like this, that its length eventually tends to zero, you might say. Okay. It seems to be zero. We will be coming to the explanation. So suppose we have this closed set 0 1. Okay. Okay. So this is this interval, right? 0 1, this interval. Now what we do, we cut the portion, this open interval we cut out from it, 1 upon 3 to 2 upon 3. Okay, 1/3 of it we cut out. Okay, and form a new family, which is, let's say, f1 except 1 upon 3, 2 upon 3. Clear? So what are we now left with? So this was eventually f1. Now we are left with this much, right? Right? This is 1 upon 3. This is 2 upon 3. Right? We are left with this much. Rather this much, because this was a closed set. Okay. Now what we do is that now we cut 1/3 from here, 1/3 from here, and make it again smaller. Okay. So what we do is we form a new set f3, which is f2 minus open interval 1 upon 9 to 2 upon 9 union 7 upon 9 to 8 upon 9. Okay. And we keep on doing this. We keep on extracting 1/3 portions from the set infinitely many times, right? Uncountably. And eventually we get a sequence of these sets, which is called the decreasing sequence of closed sets. Rather, if we form a family of each of these individual sets, then we say that particular family to be a decreasing family of closed set, better known as a Cantor set. Okay, sorry, better known as the decreasing family of closed set, not a Cantor set. Cantor set will be the intersection of these. Okay, so what we do is that we form a family of, let's say, index set I, and a very important property of this family is that fn it so see f3, which one is contained in see fn is contained in fn minus 1, again fn minus 1 is contained in fn minus 2, and so on, where f2 is contained in f1. So this is a decreasing family, right? This is a decreasing family, and if you take the intersection of all these families, we get the Cantor set C. Okay. I belongs to indexing set I, fi. This set is called the Cantor set. This set is called the Cantor set. Is it clear? Is it clear? Now see, the dropped intervals, with every formed set we are dropping intervals, right? So what are the length of those dropped intervals? Okay. So first we dropped 1/3 part, then we dropped 2019, 29th part, then we dropped 427th part. So if we keep on adding them, we get a geometric series. What is the sum of the geometric series? It is equals to 1, right? It is equals to 1. And what was the length of the, or rather, what was the measure of the set itself? The measure of the complete set was kind of 1. So ultimately, we had the measured one, we dropped the measured one. So what we are left with? 0. Measure of Cantor set is 0. Is it clear? Is it clear? Okay, details about measure you will be learning later. Okay. Is this much clear? Okay. Next we talk about sequence spaces or metric spaces of sequences. Okay. So suppose XD is a metric space. Suppose XD is a metric space. So a sequence in X is basically the function from n to x. Okay. The set of all these functions give you the sequence. Gives a sequence in metric space. Okay. We have already learned basics about these functions in real analysis. So they are kind of analogous. Okay. Okay. So one more thing. Any sequence xn converges to x. So we had these concepts in real analysis as well. So we used to say that this distance between xn and x is less than epsilon, right? Or we can say that this distance between xn and x tends to 0 as n tends to infinity. So the same definition is basically here as well, because these definitions are abbreviated from here, right? So this sequence converges to x. This basically means distance between xn and x tends to 0. Clear? Clear? But let us also write the delta epsilon definition here. Okay. Delta epsilon definition. So let XD be a metric space. Let XD be a metric space. Let Xn be a sequence of the metric space. Okay, Xn is said to converge at capital at small x belongs to capital X if and only if for all epsilon greater than 0 there exists a delta greater than 0. Sorry, if for all epsilon greater than 0 there exists n naught belongs to natural numbers such that distance between n and n naught is sorry yeah, so there exists n naught greater than 0 such that n greater than n naught implies distance between xn and x is less than epsilon, right? We can also write this that x xn belongs to the open ball centered at x and radius epsilon. So in statements we can say that xn converges to x if elements of xn eventually fall into open ball with center at x and radius epsilon. Right? Got it? Okay. Got it? So the this convergence we can also use symbols of limit. That is xn converges to x is same as writing limit xn equals to x as n tends to infinity. Okay. So these symbols are kind of analogous. Now let us study a few examples. Suppose, let's say, you have a discrete metric space. XD is a discrete metric space. Then, which sequences are convergent in a discrete metric space? See, the distance between any two elements. The distance between any two elements can either be 0 or be 1. Right? Can either be 0 or be 1. So the sequence to be converging to some point will only happen if the distance tends to 0, right? And when can the distance tend to 0? The distance can tend to 0 if it actually equals 0, right? Suppose we say that xn is a sequence from capital X, okay? So distance between xn and x, this tends to 0. What can be the only condition? See, it has two fixed values. Dx and x will have two fixed values, either 0 or 1. It cannot take values which keep on decreasing to 0. It can either take 0 or 1. So the only possible case for this to happen is if this distance equals 0. When can this distance equal 0? If xn equals x, right? If xn equals x. So can we say that if this sequence, if xn is eventually constant to x, then it converges to x. Then xn converges to x. Okay. So if xn is such a sequence that eventually becomes constant to some value, so it converges to that value. Okay. Clear? Or we can say only convergent sequences in a metric space are those which are eventually constant or constant, completely constant. Is it clear? Is it clear? Okay. Now let us see a few important things related to. Okay, let us first discuss what is a Cauchy sequence. Then we will be discussing the other things. What is a Cauchy sequence? We had studied this in under real analysis too. So let xd be a metric space. Let xd be a metric space. Xn belonging to x is a Cauchy sequence. If and only if for all epsilon greater than 0 there exists n naught belonging to natural numbers such that n and m, two natural numbers greater than n naught, implies distance between xn and xm is less than epsilon. Okay. So what does this basically mean? So the Cauchy sequence is such a sequence in which as the sequence increases, the distance between the elements of the sequence keeps on decreasing. Okay, the distance between the elements of the sequence keeps on decreasing. Now, in real metric space, with respect to usual metric, convergence and Cauchy, these two sequences uh, were biconditional statements, right? So if a sequence is convergent, it's a Cauchy sequence. If a sequence is Cauchy sequence, it's a convergent sequence. But in case of a general metric space, it does not happen. Okay. In case of a general metric space, every convergent sequence is a Cauchy sequence indeed. Okay. In a general metric space, XD, every convergent sequence is a Cauchy sequence, but every Cauchy sequence might not be a converging sequence. Okay. If every Cauchy sequence becomes a converging sequence, then we call that metric space to be a complete metric space. That's a different topic as a whole. Okay. If every Cauchy sequence in a metric space is a convergent sequence, then we call that sequence to be we call that metric space to be a complete metric space. Okay. While in any arbitrary metric space, convergent sequences are always Cauchy, and that's a very simple proof. Okay, so I'm writing it as a theorem. Okay. In a metric space XD, uh, every convergent sequence is Cauchy. Every convergent sequence is Cauchy. Now let's prove it. So proof. So let Xn be a convergent sequence from X. Okay. So what does that mean? That means there exists some value in X such that Xn converges to X. Okay. So how can we write this with delta epsilon definition? So we can say now that implies for all epsilon greater than 0, there exists some n naught natural number such that n greater than n naught implies the distance between xn and x is less than epsilon by 2, let's say. Okay. Now the same definition can also be rewritten as also for all epsilon greater than 0, there exists some n naught belongs to n such that whenever m is greater than n naught, m is another natural number, let's say, such that distance between xm and x is less than epsilon by 2. Suppose this is a sequence. This is xn0. This is say xn and this is say xn. So whatever property this will obey, this will also obey, right? Because it's a convergent sequence. So now what is distance between xn and xn? It is less than equals to distance between x and x plus distance between x and xn. So this is less than epsilon by 2, less than epsilon. So this is eventually less than epsilon. So what does that mean? Xn is a Cauchy sequence, right? Xn is a Cauchy sequence. Clear? So this is a fairly simple proof. The other proof, that is convergent sequences are Cauchy. Cauchy sequences are convergent, which happens only in case of complete metric spaces. We will do it later. Okay. Some more properties related to these convergence of sequences. Let's say, suppose you have R2 with respect to, let's say, D only. Okay, usual metrics. Okay. Suppose you have a sequence Xn and it converges to X. Suppose. Acha, every element of R2 is an ordered pair of elements, right? So let's say Xn is ordered pair Xn1, Xn2, and X is say X1 and X2. So if Xn converges to X, that basically means Xn1 converges to X1 and Xn2 converges to X2. Clear? Clear? I'm giving this as an exercise. Do prove it. You know, these are very relative theorems. For example, you know, if you have the if you take the, let's say, CD. Okay. This is the basically the complex metric space, right? So in case of CD, uh, suppose you take a sequence Zn. Suppose you take a sequence Zn, and Zn, let's say, converts to Z. So suppose Zn is xn plus iyn, and Z is x plus iy. So if Zn converges to Z, will converge to x, and yn will converge to y. Okay. So these are very relative concepts. These concepts can be directly applied to RK, CK, okay, even LP spaces also. Okay, you can apply directly to those spaces, L1, L2, L infinity. Okay. Is it clear? Is it clear? Acha, let us study one more theorem related to Cauchy sequence. Mm, that is, suppose xn is a Cauchy sequence in Rk. Okay, xn is a Cauchy sequence in Rk. So xn is basically this ordered pair, right? xn1, xn2, so on till xnk. So each of these are also Cauchy sequences. Okay, so this implies xnj is a Cauchy sequence for all I, for all j close to 1 to k. Is it clear? Understood? 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 Now let us see a very important example. That is, suppose you take L1. What is L1? L1 is the set of all those sequences. L1 is the set of all those sequences, okay, such that their sum is finite, let's say, or they converge to a finite number, or rather they are convergent. Okay. Suppose you have L1. So in L1, any sequence xn converges to x implies xnj converges to xj for all j, right? But but this is not an if and only if statement. That is, if this happens, this will also happen. That is not the case. If a sequence converges to x, then every element of that sequence will also converge to every element of the converging number or the converging value, right? But the converse is false. So let us take a counter example to prove the converse is false. It is pretty simple. Suppose you take this sequence En. What is En? En is the identity transformation, okay, of the identity function. Let's identity series. So E1 is basically this sequence 1 0 0 and so on. E2 is 0 1 and so on. Similarly, En is 0 0 1. This is the nth position. Okay. So from here it is clearly visible that Enj, okay, it tends to 0 for all j natural number. But what about this? What is distance between En and 0? Okay. What is distance between En and 0? Distance between En and 0 is basically norm of En, which is basically 1, right? For all natural numbers n. So that does not tend to 0, right? So that means En does not converge to 0. En does not converge to 0, but Enj, they converge to 0, right? So the converse is not true. Okay, converse is not true. Okay. Clear? Okay. Next we check a very important theorem related to closed set, and mind it, this theorem is really very important. Okay, that is theorem. Let's say let xd be a metric space. I'm writing this theorem with its explanation itself as the theorem. Be a metric space. Let A be a subset of X. Let Xn be a sequence of elements in A. Be a sequence of elements in A. And let Xn converge to X. Then this element to which the sequence converges, it belongs to the closure of the set. Okay, and conversely X belongs to A closure implies it must be the limit of some sequence in A. Okay, so in very simple words, A closure or A closure is the set of limits of sequences in A. Okay, that is, if you take any sequence in A, if it converges to some number, that number belongs to the closure of A, and every element in the closure of A is the limit of some sequence in A. Okay, is it clear? It's very simple, right? So now we will prove this. This proof is also fairly very simple. Okay, so just prove this. Yeah, so let an be a sequence from A, okay, and an converge to X to show that this belongs to A closure, right? Okay. So now see, this statement basically implies now an converges to X implies for all epsilon greater than 0 there exists n naught in natural number such that n greater than n naught implies distance between an and x is less than epsilon, or we can say that an belongs to the open ball with center at x and radius epsilon. Okay, also this an belongs to A, also an belongs to A, right? Because in this sequence is itself a sequence of A, so elements will obviously belong to A. So this implies u x epsilon intersection A is non-empty. So this implies X belongs to A closure. This is derived by the definition of closure of a set, right? Right. So this one is proved. So now we need to prove the converse. That is, if you have, if you choose an element from the closure of a set, then that is obviously a limit of some sequence in A. Okay. So conversely, let X belongs to A closure. We need to show there exists some sequence an from A such that an converges to X. Okay. Achha, X belongs to A closure. This implies for all r greater than 0, open ball with center at X and radius r, intersection A is non-empty. Now let R be 1 over n for all n belongs to natural numbers. Okay, we can choose any r, right? Because it is any positive r. Okay, so now ux 1 by n intersection A is non-empty. This implies that an this implies that there exists some an which is in the intersection. So this an obviously belongs to, so this implies this an obviously belongs to ux 1 by n and a. Now so this radius we considered as 1 over n, or rather we can say it like this, that uh, so there exists a sequence of these elements a. We can form a sequence of these elements n. Okay, so an, because an belongs to a, so an is a sequence of elements of a, right? Because an has been taken from a. Now what is the distance between a and x? Since an belongs to this, so an and x is less than 1 over n and obviously greater than 0, right? Now 1 over n tends to 0 as n tends to infinity, which eventually means distance between a and x tends to 0 as n tends to infinity, which eventually means that an converges to x. So we have proved our theorem. Is it clear? Is it clear? Okay. Now we move on to our next terminology, which is dense subset. Okay, dense subset. So let xd be a metric space. Let xd be a metric space. Let a belong to x. We say a is dense in x if a closure equals to x. Okay, that is if every element of the whole metric space is a closure point of a, then we say that the subset is closed, sorry, that the subset is dense in x. Is it clear? Is it clear? If we talk about example, we have q. Okay, we have q because we already know it that q closure is r, right? It is fairly simple to see. Clear? You can also say that every set is dense in itself, right? Every set is dense in itself because because every set is closed. The closure of every every metric space is dense in itself, right? You might say. Rather we cannot say that, right? We cannot generalize this statement, right? Yeah. R is a metric space. No, we can generalize this statement actually. Yeah, we can generalize this statement that suppose xd is a metric space, x is dense in itself. Yeah. Okay, let us move on to the next terminology. What is meant by a separable metric space? Okay, so a metric space xd is said to be separable if it has a countable dense subset. Okay, example R. R is a separable metric space. R is a separable metric space because what is the reason? Q is dense in R. Q is dense in R and Q is countable, right? Q is countable. R2 is also separable. R2 is also separable due to Q cross Q. Clear? Clear? Achha, what if we talk about suppose, or rather, let me take as a claim or question: is RD separable when D is a discrete metric? Is RD separable if D is a discrete metric? Let's say. See, uh, see a singleton set X, okay, where X belongs to R. This is the open ball, the centroid X and radius 1, right? And R can be written as the union of all these open balls or the singleton sets, okay, right? Right. So basically, each of these singleton sets are closed in R, but D is discrete metric. Each of these singleton sets are closed in R, right? But the family of all these singleton sets are uncountable. The family of these singleton sets are uncountable, right? So the closed subsets present in RD, where D is a discrete matrix, is uncountable. So this is non-separable. Is it clear? Is it clear? Acha, we had not discussed that why do I say that Cauchy sequences are not necessarily convergent in any arbitrary metric space. So suppose you have this metric space 0, 1, excluding 0, including 1. Okay, and you choose this sequence xn equals to 1 over n. Now xn equals to 1 over n is Cauchy. You can prove it on your own. It is fairly simple. It is fairly evident. And xn converges to 0. But 0 does not belong to x, which means xn is not convergent in x. Is not convergent in x. The limit of the sequence must belong to the metric space. If x would have been 0, 1, then this would have been convergent. Okay, so it is fairly now evident that generally Cauchy sequences are not necessarily convergent. Clear? Clear? So now we move on to the last proof of today's lecture, that is all Cauchy sequences are bounded. That is all Cauchy sequences are bounded. Okay. Last theorem: every Cauchy sequence is bounded. Okay. Okay. So a few scratch work. Let's say, what do we mean by boundedness? So by boundedness we mean that there exists some positive number. So a sequence xn is bounded implies there exists some positive number. Let's say there exists some positive number alpha such that distance between xi and xj is less than equals to alpha for all ij belonging to natural number. So every element, distance between every element of this sequence is less than alpha. Yeah. So we need to show that every Cauchy sequence is bounded. So let us assume a Cauchy sequence first. Proof. Let Xn be a Cauchy sequence in a metric space, let's say Xt. Now, what does that mean? This means that for all epsilon greater than 0, there exists a natural number n n0 such that n and m greater than n0 implies distance between xn and xm is less than epsilon. Now see, we divide this into two cases. See, case 1 and case 2. So in case 1 we deal with the complete sequence with the elements less than n0. Okay, So here we deal with the sequence xn that n starts from 1 and ends at n0. Okay, now this is a finite sequence. So this being a finite sequence, that is, there exists a finite number of elements in this set. So obviously there must be a maximum of those elements. So if we choose, let beta be the maximum of the distances where I is less than equals to 1, it is less than j, sorry, I comma j less than let's say equal to n0. Okay, so since this is a finite sequence, there exists a maximum of the distances between them, and this beta itself gives the bound of the sequence, bound of this finite sequence, right? Therefore beta is the bound of xn n equals to 1 to n0. What about this sequence xn n greater than n naught? So here the bound is epsilon, directly from the definition. Here the bound is epsilon. So what will be the bound of the both of these cases simultaneously? What bound can we choose such that both these cases are satisfied? Can we choose anything supposedly maximum between beta and epsilon? That is not the case here, right? Choosing a maximum between beta and epsilon is not the case. But what we can do necessarily is that we can choose alpha as beta plus epsilon, which is the bound of the whole sequence xn. Maximizing between beta and epsilon won't be the case. Okay, so I'm giving this to you as an exercise to check why. Exercise check why alpha cannot be alpha can't be considered as maximum between alpha and epsilon, sorry, beta and epsilon. Okay, I will be giving the answer in the next lecture. First try it yourself. Is this clear? So every Cauchy sequence is bounded and every convergent sequence is Cauchy. Okay, so every convergent sequence is Cauchy and every Cauchy sequence is bounded, which necessarily imply every convergent sequence is bounded. Every convergent sequence is bounded. Every bounded sequence may not be Cauchy. Every bounded sequence may not be Cauchy. For example, suppose you have this sequence xn equals to 1 minus 1, 1 minus 1 and so on. This is a bounded sequence, but not a Cauchy sequence. Clear? Okay. Let me give you two more properties related to sequences, and then we will be from the next lecture we will be starting from what we call complete metric spaces. Okay, so two more properties let me discuss. Property number 1. Okay, let us first declare this. So let xd be a metric space. Let xd be a metric space and xn be a sequence in X. Then point number 1, xn converges to X implies every subsequence of xn also converges to X. And point number 2, if xn is a Cauchy sequence, and has a convergent subsequence, then xn is Cauchy, sorry, convergent. Okay. You can try to prove these two as well. So with this lecture we have done this much, guys. In the next lecture we will be start about talking about complete metric spaces. Okay, so meet you guys in the next lecture.